Hello, this is Mr. Ferris again. I'm going to walk you through the second part of lesson 6.1. So you'll need your guided notes. The page number on the guided notes is 129. And on this lesson, we're going to extend working with tables, probability models, and calculate the standard deviation, as well as the variance, although, those are related. The variance is just the square of the standard deviation. But let's focus on standard deviation. And we've learned that already in the context of a data set. And you might remember that the standard deviation is sort of an average distance from the mean from all the data. Well, this isn't really data anymore. This is a random variable. So the random variable, though, does vary. It's a variable, so it does vary. It goes anywhere from 0 to 3. So what we're trying to figure out is, well, what's the average variation that we have between 0, 1, 2, and 3? And what complicates it is that these are not equally likely. There's different frequencies, there's different probabilities of these things happening. So that has to figure into our formula a little bit, as you'll see. So if it's the average deviation from the mean, then we first have to find the mean. The mean of random variable x, which is also called the expected value of x, we already found that out from a previous lesson, and that was 1.5 heads. So on average, you get 1.5 heads. And of course, because this is a symmetric probability distribution, the mean is going to be halfway between 1 and 2. So that would have been an easy one to do in your head just because this was a symmetric probability distribution. But we did the calculation, and that's what we got earlier. Now we want to find the average deviation from the mean. So the standard deviation of random variable x, or sometimes you'll see SD, capital X, is going to be the average deviation, or the typical deviation from the mean. The mean is 1.5. So the first thing we'd want to do is find, well, what are the deviations from the mean? So I'm going to leave some spaces in here, and I'd like you to do that as well. So the first possible x is 0. So how far does 0 vary from the mean? Well, we can just subtract. Take 0 minus 1.5. Another deviation from the mean would be from the second possible outcome, 1. To find the deviation from the mean, we'd take 1 minus 1.5. And then the third deviation from the mean would be how far 2 is from 1.5. So 2 minus 1.5. Then the last deviation comes from 3 minus the mean. So these would be all the deviations from the mean. And if you've got a really good memory, you'll remember that we want to square these and then take the square root later. That's how we get these all to be positive, because average distance from the mean has to be positive. So we're going to square them just like we did for the standard deviation formula back in chapter 2 or whatever that was. And then we're going to add these because we want like usually we would add them up and divide by n minus 1. Well, here's where it gets a little different, because we're not going to add them up and divide by n minus 1 because these are not equally likely. There's a different probability for each of these things to happen, a different frequency. So we can't just add these up and divide by n minus 1 because we have to put the weights, so to speak, or the probabilities, the frequencies in there. So what we do is we take each of these differences squared and multiply it times the probability of that thing happening. So if the probability of 0 happening was 0.125. The probability of 1 happening was 0.375. The probability of 2 happening was 0.375. And by multiplying each of these differences squared by the probability of them happening, it gives each of them the proper weight for this computation. And because we are weighting them, then we don't add them up and divide by n minus 1, we just add them up. The division by n minus 1 has been mathematically kind of accounted for by multiplying by these weights or these probabilities. So that would be the sum of all the squared differences times the probabilities. That right there, if we left it as is, would be the variance. But we want standard deviation. So because we want standard deviation, we're going to want to take the square root of all of that. We're going to take the square root of all of that. And that should give us the answer that we got. I think we did this on the calculator in the last lesson. And we got an answer of approximately 0.8660. That was the standard deviation number that came up on our graphing calculators when we did kind of the shortcut method. But this is the work behind that shortcut method. It's still the sum of differences squared. The nuance is we're now multiplying each of those terms by the probabilities before we add them up and take the square root. And that gets us back to the standard deviation. And then the variance for this random variable, which the variance symbol is sigma squared. So sigma squared of x, or the variance of x, is going to be 0.8660 squared, which is 0.75. So probably what we'll do is, in the future, is we will find the standard deviation first from a graphing calculator. We won't really do all this work. And then we'll square that to get the variance. If we have to get the variance, we can do it that way. So from this point on, I wanted to show you where it comes from, of course, but from this point on, you're going to get the standard deviation right off of your graphing calculator, like we did in the last lesson. All right. How do you interpret the standard deviation? Well, I already did. The standard deviation interpretation, this is the typical, and you can even say average if you want to. The typical deviation from the mean of x. Now, of course, when you're writing this in a problem, you might have to include context. So if this is a story that has a little, I guess this is technically a story, so I guess we could say that the average variation that the outcomes 0, 1, 2, and 3 have from the mean of the number of heads, which is 1.5, is about 0.8660. So we could still include context. It gets a little cumbersome to write all that out, but that would be the interpretation. All right, so we could practice this, and so what I'd like you to do right now, believe it or not, is to pause this video. Pause this video, and I would like you to find the mean, or the expected value, and the standard deviation for both of these. So pause the video, use your graphing calculator like we did in the last lesson. You're going to use list 1 and list 2, and find the mean and standard deviation. So push pause, find those two answers, and then we'll check them when you resume. All right, so if you did what I asked you, which I hope you did, you should have found the expected value to be exactly the same. These are both games from a roulette wheel and different kinds of bets that you can make on a roulette wheel, and it turns out the expected value for both of these is exactly the same. It's about -5 cents. So it's about a nickel, roughly a nickel. Which, if you would interpret that, that means that you're going to lose. When you play roulette, either bet, doesn't matter whether it's the red-black bet or the corner bet, no matter which bet you use or you make, you're going to lose about a nickel every time you play on average in the long run. But the standard deviations are quite a bit different. For the red-black bet, the standard deviation is right about $1, almost $1. Whereas the standard deviation for a corner bet, because it's more risky, is about $2.76. So therein you have the difference between these two bets. They both have the same outcome in the long run. However, you do have the possibility of making more money, every once in a while, not very often, but every once in a while you have a chance of making more money with a corner bet, which means it's more risky, and therefore the standard deviation is a lot higher, a lot more variation between the two outcomes that you can have. So the other example that you can do, I would ask you to go back and calculate both the mean. Let's see, it says, calculate and interpret. So you're gonna just calculate the standard deviation and interpret it, not the mean. And so when you go back to the problem in the previous page about the APGAR scores, it's a longer table. If you would pause and do that again, this would be a great time to practice and get feedback immediately. So pause the video, go back and calculate the standard deviation for the APGAR scores, and then write an interpretation. So pause. When you play back, I will give you the answer. All right, the standard deviation for the APGAR scores should be approximately 1.437. Now, interpreting it's kind of weird because these are just scores. They're not like inches, feet, dollars, anything like that. But we can still say something like the typical variation, or if you like average, you can do that, the average variation, typical variation in APGAR scores from the mean APGAR score which was just a little over 8, if you recall. So the typical variation in APGAR scores from the mean APGAR score of 8.128 is approximately 1.437. So on average, APGAR scores are going to vary by about one and a half. I don't know even what you call it. 1.5 scores, 1.5 whole numbers. They don't really have a unit there. So there you go. That's standard deviation. We still talk in the same language. It's the typical variation from the mean. But now we're just doing it with random variables, and we have different contexts just like we do in other places. There are 2 dangers, however, when you're using your graphing calculator. Calculator's great. It's quick and easy. It gives you answers. But on an AP test, you typically always have to show work for calculations. So just don't forget in a free response question to show work. Now, I know some of these are like, man, are you kidding me? You have to show all this work? Because look at this one up here. You mean I have to show all this work right here? That's a lot of work to show. Well, the good news is they will let you get by with just the beginnings. So I'm going to write in here at least the beginning of the calculation. So what you can do is write like the square root of 0 minus 1.5 squared times 0.125. And you could even do plus ... and then say that that's approximately equal to 0.8660. If you just get it started and put ... that's going to be fine. The other danger is that when you change your calculator to a frequency of list 2, you got to remember that when you do regular data calculations, that really needs to be a frequency of 1. You normally just need 1 of each number in the data set when you're calculating. But when we change it to a frequency of list 2, we're making list 2 the probability list, the frequencies, or the probabilities. And so we always need to remember to change that back to just plain old 1 when we're doing regular data calculations. So just beware that you have changed the frequency to list 2, and that could give you an error message in the future if you don't change it back. All right, here's another kind of random variable. This is the second page of notes. Another kind of random variable is called a continuous. So far, we've just been dealing with discrete random variables. Discrete random variables are countable. Like with the APGAR scores, the scores can be from 1 to whatever, and they're countable. With the flipping a coin, we only flip 3 coins, so the outcomes could be 0 heads, 1 head, 2 heads, 3 heads. There's only 4 things that can happen. Those are countable. So continuous must be some sort of a random variable whose outcomes are not countable. That would be our definition. Some kind of a random variable, so it's still something that happens kind of on a random basis, but the outcomes have an uncountable. Now you could also say an infinite. That's really what we're talking about, an uncountable number or an infinite number of possibilities. So try to think about a variable that behaves, sort of randomly. And so the outcomes, though, when you try to count all the possible outcomes, you can't. There's too many possibilities. Well, one example might be if we measured everybody's heights, but we maybe didn't say to round off to the nearest centimeter. Well, if you have a very, very accurate mechanism, you can get it down to the 10th of a centimeter, 100th of a centimeter, 1,000th of a centimeter, microns. I mean, you could get it down to where you almost couldn't count all the outcomes. So height, technically, if you don't round off to the nearest whole number or something like that, could be considered a continuous random variable. How about the time it takes to run some sort of a race, like maybe a 5K race? If you have a bunch of runners and they're all running a 5K race or maybe even a marathon, if you have a really accurate stopwatch, the possible times to run a 5K could be, virtually uncountable. Maybe it's really thousands or tens of thousands, but that's almost uncountable. We would consider that to be a continuous random variable. How about your foot length? How long is your foot? Well, I suppose most of the time when we practically measure our feet length, we round off. Even if you round off to maybe, what would it be, 20, that would be more like 56.2 centimeters or something like that. You might round off. But, it really could be 52.6259666296252. And so the number of foot lengths could typically, theoretically, be completely infinite. There could be no limit to that. So here we have a couple interesting questions here. Is it possible to have a shoe size of 8? Well, of course. A lot of you probably have a shoe size of 8. That is a discrete random variable. Shoe sizes come in halves, but they're countable. They're very countable. So 5, 5.5, 6, 6.5, 7, 7.5, 8, 8.5. Those are countable. But what about a foot length that's exactly 8? Is it possible to have a foot length of exactly 8? I'm going to suggest to you that that's not possible. It's not possible to have a foot length of 8 inches or even 12 inches or whatever, because think about that. To be 8 inches, we're talking about it has to be 8.000000000. Exactly 8 means it's not any tiny bit higher or lower, and that's really impossible. That is not possible to have a foot length that's exactly that, because you would have to have exactly 0 tenths, 0 hundredths, 0 thousandths, 0 ten thousandths, and that's, in theory, I don't think that's really possible. So how many possible foot lengths are there? I would say there's an infinity. How would we graph that? Well, here's where maybe you can imagine if we graphed it, and we were graphing, lots and lots of people, we might want to, instead of using a dot plot or something, could you imagine that maybe foot lengths would be approximately normal, and instead of doing a dot plot or something like that, or even a histogram, maybe we'd want to use a model like a normal model, perhaps. And a lot of lengths, whether it's feet length or heights or weights, a lot of them come out to be relatively normal. So that is how we find probabilities. We hope, and for a high school class in stats, you're going to have data and random variables that are going to be normally distributed. So how are we going to find probabilities of continuous? We're going to use a normal model. And then one little quirky thing about normal models, if we were graphing, let's say, heights or foot lengths or whatever, let's say we had a number right there that's an A. If you were shading and trying to find the probability that x is less than A versus less than or equal to A, the only difference, of course, is that one of those is including the boundary and the other one is not including the boundary. So the question becomes, how much area does that boundary add to an answer when you're shading below? Well, that boundary is a segment. And if you have a good, decent geometric background, a segment has no area. A segment is a one-dimensional shape, and it has no area. Area is only for two-dimensional shapes. So there is no difference. There is no difference. These are the same. So we don't make any designation of a difference between saying less than A or less than or equal to A, because in a continuous random variable world, they're going to give you exactly the same area, because the only difference really is just a segment or not a segment, and segments have no area at all. So just make sure that you don't have to worry about that. You can say less than A, you can say less than or equal to, and it will mean the same thing. All right, so let's do a weight problem. And fortunately, when you read this problem, it tells you that weights of 3-year-old girls do follow a normal distribution. So we get to review some normal distribution stuff here. So this is actually quite nice coming up here close to the final exam. We get a built-in final exam review on normal models. So it says that the mean of 3-year-old females is 30.7. This would be pounds. And then the standard deviation is 3.6. And now they want us to know the probability that a female weighs at least 30 pounds. So at least 30 pounds is going to be just a little bit to the left of the mean. So we would expect this answer, if it's at least 30 pounds, to be a little bit over 50%. So if you get the cobwebs out of how you do this, there's a command on your calculator under second vars. It's the distribution menu. And we want to pick normal CDF. Normal CDF is how you find the area under a normal curve. We always want to start with the left boundary. The left boundary of that area, since I drew it, is clear. Well, actually, I didn't label that part. That boundary is 30. So the left edge or the left boundary is 30. The right boundary is technically infinity, so we would type in some big number. That would be the right boundary of our area. And then we would type in the mean of 30.7. and the standard deviation of 3.6. Some of your calculators, this will be vertical, and these will be prompts. But when you're writing an answer, of course, we want to label our calculator work so we don't get dinged for no work. And if you hit enter, you should get approximately 82%. Oh, no, it's not quite that high, 57, 58%. Should be just a little over half, so that seems to agree with my sketch. So about 57, 58%. All right, between 20 and 25. All right, I'm going to let you do that one. You're still going to use the same command, normal CDF, but you have a couple things to change. So push pause and type this in your calculator, and then I'll show you what the answer is. All right, if you push pause and did it yourself, of course, you're going to show the work, normal CDF. Left boundary now is 25. Right boundary is now 35. With a mean of 30.7 again. Standard deviation of 3.6 again. And that's the one that I said earlier, 82.7%. So that's going to be a little bigger area there. And then last question, again, just a little review that we're now working this backwards. They want to find the spot where K is, and less than K is 80%. Well, 80% is pretty high. So K must be out here to the right, because less than K would be most of the area. So K should be above the mean of 30.7 somewhere. Well, when you know the area and you're working it backwards, this is a job for inverse norm. Inverse norm works backwards from the area. So depending on your calculator and what operating system you have, usually the percent left is what's asked for first. And then you want to write the mean and standard deviation, again, followed by commas. And when you type inverse norm of 0.8 with the mean and the standard deviation, then it should spit out the value of K. And we expect it to be a little bigger than 30.7, and sure enough, it's like 33.7 pounds. That would be the boundary for an area of 80% to the left. So we get to use a little bit of normal model calculations with this chapter, because a lot of our continuous random variables will be normally distributed. So you get a little practice at that. So that's section 5 or section 6.1b, I guess, the second half of 6.1. And if you do your practice problems on homework, that should give you some good review, and be sure to come to class with any questions you have. Talk to you later.